Okay, well, what if I want to find the area under a function that's not a nice geometric figure? Okay, so in pre-cal, you learned how to find a definite integral as long as the function was a really nice geometric figure. For instance, a circle or a triangle or a rectangle or something like that. Well, this is where the idea of a Riemann sum comes into play, and I'll illustrate that here using an increasing function. Okay, so if I have an increasing function here, then what I want to do in order to find the area under that curve is I want to split this interval from A to B. I'm going to consider this to be B. I want to split it into subintervals. And so I'm just going to take points here on the x-axis that are in between A and B. And however many that I take will depend on how good the approximation to the area is. And we'll talk more about that a little bit later. So there's a couple of choices here if I want to use a rectangle. The first is to use the left endpoint from any subinterval. Oops, sorry about that. The left endpoint. So if I choose the left endpoint in this first subinterval, then that's really not going to create a rectangle at all. From the next subinterval, I'm going to choose the left endpoint, and I'm going to make a rectangle. From the next subinterval, I'm going to again choose the left endpoint up there on the function, and that's going to create a rectangle. And then in the next subinterval, the left endpoint. Okay, and then from the last subinterval, the left endpoint. Okay, so what I have here is these areas of the rectangle that help me approximate the area underneath the curve. Now, what you should hopefully notice is that by using the left endpoint, so this is where we use the left endpoint, we didn't capture all of the area. And so that leads us to filling in the first blank here. If a function is increasing, then a left Riemann sum is going to under-approximate the area under the curve, or the definite integral. Okay, if I instead take the right endpoint from every subinterval, so I'm going to try to draw the same figure here, increasing function. Here's B, here's A. I'm going to try to take the same number of subintervals if I can. And now this time I'm going to take the right endpoint. So from A to this first tick mark, I'm going to take the tick mark and make a rectangle there, like that. Then I'm going to have a rectangle here, come down and across to make my rectangle. Then I'm going to go up to the function and over for a rectangle, up to the function, over for a rectangle, and then up and over to create my rectangle. And now hopefully what you're noticing, I'll use a different color here, now you should be noticing that we are over approximating the area under the curve. Okay, so what that means is that if a function is increasing, and notice that both of these functions were increasing in my picture, then a right Riemann sum will over approximate the exact value of the integral or the area under the curve. Okay, well, what if the function is decreasing? Do you think it's going to be the same? Okay, well, if you answered no, then you're correct. So if I have a decreasing function, okay, so let's draw a decreasing function here. And let's first of all use the left endpoint of every subinterval. So here are my subintervals. I'm not creating a lot of subintervals, but just enough to kind of illustrate the point here. So I'll use green again for our left Riemann sum. Then I'm going to take the left endpoint. So the left endpoint of the first subinterval is going to be there. The left endpoint for that subinterval is there. The left endpoint here is there. And then here to here. And so hopefully what you notice is that, again, I am over approximating the area under my black curve. Okay, so if a function is decreasing, then the left Riemann sum will over approximate the area under the curve. Okay, similarly, if I draw a decreasing function and then use the right endpoints to create my rectangles, then this is going to be, as you're about to see, an under approximation. So let's again use the same color. We're going to use the right endpoint here. Okay, so you can see there's an under approximation, there's an under approximation. Try to get it as close as I can. And so this area in pink is not enough to be the entire area under the curve, and so this is an under approximation. So it'll under approximate the area under the curve. Okay, so you do need to have this memorized. I had a student a couple of years ago come up with a good acronym to kind of help us out, and that acronym is I love you, Drew. And so what that means is kind of goofy, but it helps. It means increasing, so this stands for increasing left is an under approximation, and decreasing right is also an under. And so you can fill in the blanks for the other two cases. So if you can remember I love you, Drew, you can determine is it an over approximation or is it an under approximation.